Okay, so let us begin. It's a pleasure to have Professor Misao Sasaki for this week's Majorana-Raychaudhuri special seminar session. And he's going to talk about primordial inflation, known unknowns, known knowns, known unknowns, and unknown unknowns.
Thank you. Okay, let me just start. This may be maybe a little bit basic for those people who knows inflation, but I try to be sort of a bit general. But anyway, if you have any questions, comments, or anything, please raise your hands. I guess it's okay for the people audience to say something during my talk, right, Anish? Is
Yes,
it allowed?
yeah, sure.
Okay, yeah. So then stop me if somebody raise hands. Okay. All right. So let me start. First of all, let me just explain what inflation is. As many of you know, that inflation is the quasi-exponential expansion of the universe at its very early stage, and perhaps or hopefully at very, very early time, when the time is like 10 to minus 36 seconds after Big Bang. I mean, after the universe was actually born. And in that case, as we see later, that maybe there's a chance to see the primordial gravitational wave perturbations, which are the space-time quantum fluctuations of the space-time. Anyway, it was originally meant to solve the initial condition problems in Big Bang cosmology, so-called the singularity problem, horizon and flatness problem, and so on and so forth. However, now we sort of realize that if any of them can be said to be solved, depends on how you define the problem. So, right now, this initial sort of motivations were important in the beginning, but now it's much less important. Anyway, the most important things that now we realize that quantum fluctuations, that quantum vacuum fluctuations during inflation turned out play the most important role. They give the initial condition for all the structures in the universe, including us, everything. It's the source of everything which is non-trivial in our universe. And this has been sort of almost shown to be correct by the observational data, but we still need one more sort of evidence, which is the gravitational wave background, as I told you. And if we are lucky enough, and if the energy scale of inflation was high enough, then we will be able to see this in the very near future. Okay, now this is the standard picture of inflation to Big Bang. So somehow inflation began. So again, I'm not talking about the beginning of inflation. Assuming that inflation started somewhere and then continued for sufficiently long time, which we usually count by the number of e-folds, and as we soon see it, the number of e-folds we need is more than say 50 or 60, but above that we don't know. Maybe it's just about the number of e-folds 60, or maybe 100, maybe 1,000, maybe almost infinite. Anyway, but we know that the inflation must end, and it's very important for inflation to end, and that determines essentially the beginning of our universe. After inflation, the vacuum energy is converted to thermal energy. This process is called reheating, although probably perhaps there was no heating before inflation, so it was kind of the first time the universe was heated, but it is called reheating. And the hot Big Bang universe is realized, and the picture on the right hand side is just schematic sort of diagram of a time versus density, and density of the universe during inflation. It is slowly probably changing, but not much. So almost constant. Density is almost constant, and which gives rise to the exponential expansion. Then after inflation, we expect this inflation, the field that drives inflation, which is called inflaton, to go through sort of underdamped. Oh yes, it's a which was the correct terminology. I forgot, but the damped oscillation anyway. It undergoes damped oscillation, and then the universe would behave like a matter-dominated stage, but this stage may be short or long. We don't really know. Eventually, they are converted to thermal energy, and the universe become radiation-dominated, very hot and dense universe. And that's we can think of this epoch as the beginning of hot Big Bang universe, and so the initial condition for the hot Big Bang universe is given by inflation. Now, a few comments or points which you should keep in mind is usually, or maybe at least in the initial as an initial motivation, people say that the homogeneity and isotropy of the universe, essentially global homogeneity and isotropy on average, are a result of inflation. That was some kind of a belief spread in the society. Of course, there is such a kind of some component of such a thing is true, but still, in most cases, when you discuss inflation, homogeneity and isotropy are the assumptions, most important assumption, not a consequence. So that's one thing you should keep in mind. Also, now, after 1990s or so, that people start to talk about various different higher dimensional theories and the dimensional reduction and so on and so forth, especially in string theory context. And in string theory, people started to talk about various different frames. Frames can be, like string frame or some other frame, or in the sort of traditional modified gravity sense. Then people might call some frame where the gravitational action is highly non-trivial, not different from the Einstein, and which is quite often called Jordan frame. While you could do some conformal transformation in many cases to bring that into Einstein frame. Now, depending on this the transformation variable, the expansion behavior of the universe can be completely different. So the only way to define inflation or a quasi-exponential expansion is to define it in certain frame. My sort of a tentative the definition is that we, let's assume that there exists an Einstein frame or some approximate Einstein frame. Then we can say universe undergoes inflation if the expansion in that Einstein frame experiences quasi-exponential expansion. And in this Einstein frame, at least we think that this 50 or 60 number of e-folds is necessary to solve the so-called horizon problem. Here, the horizon problem is not to mean the homogeneous and isotropy, but it's the some correlations of the large scale fluctuations. And again, as I keep saying that we don't care what happened before inflation. The whole point of inflation, important point of inflation, is that the predictions are almost independent of initial conditions. Of course, there are models that does depend on initial conditions, but many models of inflation, it is independent. This is just like the case of Big Bang universe, hot Big Bang universe, where you assume a thermal equilibrium complete thermal equilibrium in the early universe. And once you assume the thermal equilibrium, then you don't care what kind of initial condition the universe had. Once it reaches thermal equilibrium, you forget about all the initial conditions. So in that sense, it's similar to that. In the case of inflation, once the universe is dominated by so-called vacuum energy, then a universe essentially forget the memory of the previous stage. Okay, so as I said, that's this point 1 and 2 basic assumptions, or maybe you could call a definition of inflation. Anyway, so this is something maybe you can keep in mind. Okay, let me just talk about some space-time diagram. So this is very famous space-time or time space diagram. The horizontal axis is the log of scale factor of the universe, which is the number of efforts, and the vertical axis is the log of the lengths, the physical lengths. Then during inflation, you have this blue line, the Hubble horizon scale, which essentially determines the causal regions in local causal regions at each instant of time. This horizon scale is almost constant during inflation, and it undergoes some reheating process, which might be, as I said, some matter-dominated stage or something else. But anyway, eventually the universe becomes radiation-dominated again, and quite recently it started to become matter-dominated, and now again maybe some dark energy or this vacuum energy-dominated universe today. But I'm not touching anything close to the current universe. I'm focusing on this primordial inflation. There, as you could see from this figure, that you need and this well, by the way, the horizon no, sorry, the green lines represent the co-moving scale, which is a scale which expands with the expansion of time. So if we have to sort of explain all the physics occurring today to be something happen during inflation causally, then the current Hubble horizon scale, which is it's not inverse, must be within a horizon patch during inflation, and which determines the minimum number of E-folds, and which is about 50 or 60 number of E-folds. And as I said, if further we assume some a definite stage inflationary Hubble parameter expansion rate during inflation to be some definite value, which let's say correspond to this hopefully this time to 10 minus 36 and so on and so forth, then Hubble parameter is compared to the current Hubble parameters, it's greater than exponential 10 to 20 or something. Actually, if you assume the purely radiation dominant universe from the end of inflation today until today, then this half of this 120 actually gives you the minimum number you need for inflation. So this is where this number of 60 E-folds number 60 E-folds comes from, and you could see that if the Hubble parameter becomes lower and lower, or the Hubble scale during inflation becomes larger and larger, then number of E-folds necessarily becomes smaller and smaller. But anyway, this is the length scales of the inflation in the universe. Okay. Now, this is the simple explanation of why the inflation can explain flatness of the universe. That whatever the universe you have, if the universe expands a huge factor, let's say by a factor of 10 to 30 or so, which is like the number of E-folds of 60, 70 or something, then then the size of observable universe could be much smaller region of this total gigantic universe. And if you look at the local scale, local regions of this gigantic universe, then apparently the curvature of space curvature looks very small, and therefore it looks perfectly flat. So in this sense, flatness can be explained by inflation. But as I said, this depends on this assumption that you had huge expansion. So the huge number of expansion, number of V-folds of inflation. And if the inflation is not that long and has some very small, short duration of time, then this flatness may not be explained. So inflation may not always imply flatness. But if we find flat universe, most probably this is due to inflation. Okay. Now, let me then go to dynamics. And the most important thing is, as I said, quantum vacuum fluctuations. And there has been lots of work on this, but let me just explain in the most simple terms that first of all, forget about the gravity or anything, just focus on some fluctuations of a scalar field which drives inflation. And inside, let's say, inside the horizon scale. Oh, by the way, so it's important if you discuss physics inside this scale inside the Hubble horizon, then at leading order, you can actually ignore gravity. This is exactly like what we experience in today. In this a scale of our human life, we don't have to worry about the expansion of the universe. Then we can discuss all the quantum physics and quantum field theory and everything in the flat space, which means that we ignore the expansion of the universe. And so that approximation where the expansion meaning you ignore the gravitational effect. That's true also on a very small scale. On this scale, interaction with gravity is very weak. So although we have some non-trivial gravity, that's why the Earth is held as almost sphere, and we are going around the sun and so on and so forth. But still, we can ignore gravity when we evaluate quantum vacuum fluctuation. So it's true here. Let's just forget about the quantum effect, but let's take into account the expansion rate, because different from our case where we don't care, how much. Sorry. Our time scale is much shorter than Hubble time, but now we are interested in scale which is comparable or sometimes greater than the Hubble's time scale. Therefore, let's just take into account the expansion of the background expansion, but ignore the gravity. Then the equation motion of fluctuation becomes something like this. Which also assumes that the mass of inflaton is negligible. This assumption is true in some cases, and it may not be true in some models, but here let me focus on the simple models, where you can ignore the mass, the charm of the scalar field at the leading order approximation. Anyway, in this approximation, delta phi behaves like a massless field in expanding universe, and this linear term linear in the time derivative is due to the expansion of the universe, which causes friction, or essentially which causes the decrease in energy density. Excuse me. And 3 is because our dimensions, spatial dimension 3. And this omega square is essentially the k square. The k square is moving wave number divided by the scale factor a square. And as you could see, in the early universe, when a is small, omega square is very large, but a eventually expands and becomes very large, and omega square becomes small. And this is sort of always the case for any expanding universe, but special for the inflation is the scale factor behaves like exponential expansion. So the decrease in omega square is very rapid. It's a very rapid decrease in omega square, and this, because of this, in the beginning, when the omega square is very large, then you have essentially oscillatory behavior of the delta phi. But as universe expands, this decreases very rapidly to zero. And for during this process, delta phi gets frozen. And I have made some small sort of a movie of this, although I don't know whether it looks okay. But so initially just expand oscillating, but at this omega square, this is effectively the curvature of the this oscillation, and this oscillation, as I said, it's curvature of oscillation decrease very rapidly and go to zero, and then oscillation freezes up. This freezing up occurs when the omega becomes smaller than h. So essentially this means that when the scale, the fluctuation scale is smaller than h, or the length scale is greater than Hubble scale, which we call it super horizon scale, super Hubble horizon scale, or super horizon in short scales. And this is the reason why these frozen fluctuation now turns into a gravitational potential perturbations, as I will show you soon, and which causes all the which is the origin of all the structures of the universe. In the case of tensor or gravitational wave perturbations, which is genuine space-time fluctuations, they follow this exactly the same equation like this, or maybe you should call this should be regarded as actually the equation of motion for the tensor modes, scale space-time fluctuation. But anyway, they do satisfy exactly the same equation, and they would also be frozen and appears as a gravitational wave background in a current universe. Although the amplitude, unfortunately, seems to be fairly small, so it may not be so easy to detect them. But we have a hope that we will see some trace of those remaining of the remnants of this tensor perturbations. I will mention it later. Anyway, so why this fluctuation can actually cause becomes the origin of perturbation? Again, the essence is the end of inflation. If the inflation doesn't end, then nothing happens. It just continues to be frozen, and that's all you have. However, when the universe inflation ends and the universe turns to a hot Big Bang universe, then all those fluctuations contained in the delta phi, this vacuum fluctuation, frozen fluctuation delta phi, turns into a so-called curvature perturbation, and which is essentially gravitational potential perturbation. The mechanism is this. So during the inflation, as I said, you could ignore the gravity and you can consider some fluctuation, vacuum fluctuation delta phi. From the general relativistic point of view, this is essentially equal to taking the gauge in which the curvature perturbation, or the any fluctuations in the metric, in the three-dimensional metric, is set to zero. So in this gauge, or in this slicing, you have some vacuum fluctuation delta phi. However, the end of inflation is determined by the value of scale field, as locally the scale field is one which determines physics. Therefore, end of inflation surface is the surface on which delta phi is homogeneous. which means you have some a hypersurface time slice, which is different from this the so-called flat slicing, and this difference gives rise to, once you do transformation to this the flat slicing to slicing where the delta phi is 0, then you introduce some curvature perturbation or metric perturbation in that frame, in that slice, time slice. This is the source of all the fluctuations in our universe. Therefore, again, I have to stress that the end of inflation is what determines everything. And in this, this is the simple case of the single field slow roll inflation. But in many models of inflation, this is true. So unless you define how the inflation ends, actually you cannot talk about what kind of curvature perturbation or what kind of structure you would form in the universe after inflation. Okay. All right. So it's a bit more about generic prediction of inflation, especially in this case, slow roll inflation. Slow roll means that the inflation roll. Maybe I should have done. I should have explained a little bit more. So during inflation, essentially it's the energy density is vacuum energy dominated, and the kinetic energy is very small, and this is called slow roll inflation. In that slow roll inflation, unless you tune the initial values in a particular value, usually the number of equals is much greater than 100, and which means that the universe, our universe, the current universe, should not have any curvature, spatial curvature. So as you would expect in this scenario, the spatially flat universe. You have some questions? Okay. Sorry. No? Okay. So then also because of this very slow roll motion, all these fluctuations essentially is independent of scale. If you assume h to be a constant, upper parameter to be constant during inflation, then this freeze out occurs for all the co-moving frequency as soon as they cross the Hubble scale, which means you essentially have the fluctuation spectrum or scale invariant, independent of k. So scale invariant spectrum. And so this is almost scale invariant and adiabatic because it's a vacuum fluctuation, and this is the only source of fluctuation in the universe. Therefore, it is called adiabatic. And Gaussianity comes from the vacuum fluctuation, nature of vacuum fluctuation. And so this is the fluctuation you would expect. And as many of you know that this is perfectly consistent with the observations. Now, the same is true for the tensor perturbations. And in this case, actually prediction is more general than just slow roll inflation, but you expect the almost scale invariant Gaussian primordial tensor perturbations. And this is the most important sort of predictions of inflation or slow roll inflation. The more quantitatively, the amplitude of curvature perturbation is given by this formula h squared 2 pi phi dot. Phi dot is the velocity of the scalar field, and measured at the time when this scale sort of crossed the horizon during inflation, as we have seen. It's the when the scale cross the horizon, then everything freezes out. So everything is determined by fluctuation amplitude at this stage, and this is this tells you how big the amplitude of curvature perturbation is. Power spectrum index. This is the how this power spectrum, which is square of this, behaves in respect with respect to K. As I said, it's almost scale invariant, and from some historical reason, this power of K is usually written as ns minus 1. So ns equal 1 is a scale invariant spectrum in the case of this scalar type perturbations. And ns minus 1 is given by essentially the second derivative minus the first derivative square of the potential. So depending on which one wins and so on suppose, and whether this dw prime is positive or negative, this change the sign. But apparently you see, for example, this v prime, the first derivative always gives rise to negative contribution, which tells you that if you just assume that v double prime is, let's say, two terms are about the same order of magnitude, and if you assume the v double prime to be either negative or positive, can be either negative or positive, then you would expect usually the negative ns minus 1 negative spectrum, which is slightly red. So if the k goes to small value, the amplitude increases. In the case of tensor perturbations, again, this slightly red, but this now because we don't have any historical reason to put this nt minus 1, so you just assume this power spectrum to be k to the power of nt, and nt is almost 0, but which is small, but actually negative and small negative value for this slow inflation case. And actually the negative value is related to the amplitude of tensor to scalar ratio, and which is a very important observational quantity. And if we actually see this a spectrum index, and if this is consistent with this ratio of the tensor to scalar ratio, then with this formula, then we have a very strong kind of evidence for single field slow inflation. Okay, now observational data tells us, as we all know, is given by this Planck, originally the Kavli, and then WMAP, and then now finally we have this very fine a CMB map of by Planck, and this fluctuations is due to the fluctuations in the curvature perturbation, and as this dots are the observational data, and red is some model which is determined by only a few number of parameters, and as you could see, all these Planck data fits very well with some model of inflation, and which tells us that it is almost certain that the universe experienced inflation in the very universe. Okay, now the result, actually, if you use this, interpret this as the fluctuations coming from inflation, then the fact that the curvature perturbation is about 10 to minus 5, which is the observational result, tells us the energy scale of inflation can be 10 to 16 GeV. It can be always smaller, but essentially this is a sort of a maximum value we can get. For the parallel index, spectrum index, this is known to be very precise, to be about minus 0.035 or so, which means again, as I said, either you have a very large negative contribution from v double prime if the v prime over v square is negligible, or if the both are essentially the same, then both of terms they sort of contribute slightly to negative values, and the universe the spectrum index is slightly red. As for the tensor perturbations, of course, we haven't seen anything, and hopefully this can be observed by future observations. Very recently, I had very bad news about this CMB S4 project that it was not approved by NASA or something. But anyway, hopefully this can project can revive again, and we have some chance to see this in near future.
And
Now going,
sorry,
yes,
sorry. Yes, and what is the status of Litbird in Japan?
Lightbird, I actually a passed so-called a phase A test, and so well actually you should call it the phase A. So it is approved by JAXA, and they within they have given this Lightbird people, I don't know how many years, but probably 4 or 5 years, and within that years that they have to show that they actually have sufficiently, good how say a experimental tools which can be launched with a rocket and the satellite, and once this is can be approved, then they have a launch. So if everything goes well, we think that the launch will be within a 7-8 years, hopefully. Yes, let's say 1332, and I mean 2032. That's the current status. Yes. Okay.
Yeah, thank you.
All right. Yeah. And as again, maybe many people know that the Planck, the final so legacy data, which by which you can put a strong constraints on the single field slow inflation models, and this is the result. And Primordial tilt is determined to be very, very high accuracy to approximately 0.965. The tensor to scale ratio is apparently less than 0.05 or smaller, but we still don't know whether it is much, much smaller than 0.05 or of order of 0.01. If it is order of 0.01, then there's a chance that we will see this in this next 10 years or so. Anyway, so the scale spectral index is 0.965. Tensor to scale ratio is less than 0.05. And this actually means that the energy scale inflation is slightly less than 10 to 16 GeV. Now, this, and also as you could easily see, that simplest model of inflation model, which was originally proposed by Linde, this so-called chaotic inflation model, whether it's pi square, pi cube, whatever. But anyway, if you assume the positive a polynomial value for the potential, those potential are essentially almost excluded. So, and in particular, the simplest case of phi square. So what are implications? Of course, the most important message again is that inflation is the origin of all structures in the universe because of those vacuum fluctuations. And again, to summarize, the scalar spectrum index is less than unity at 5 sigma level. Tensor to scale ratio is definitely less than 0.1, implies the energy scale of inflation to be less than 10 to 16 GeV. And simple canonical models are almost excluded. The Stravinsky model, so-called Stravinsky model, which is the some modified gravity model, essentially given by the R plus R square, where R is the Ricci scalar. This model seems to fit best, as you could see from this. This R square inflation is here. Well, depending on number of people, can change the spectrum index can change, but the tensor to scale ratio is approximately 0.01. and which is the prediction of this model, and which seems to fit very well with the data, but we don't know why, because if this is due to some correction to gravity or some modified gravity, why the theory stops at R square correction is a completely unknown thing. We need some, if this is really the model, we need to understand the origin of this model. I haven't touched this much, but so this FNL is the sort of the parameter which parameterize the non-Gaussianity of this curvature fluctuations, and the single field slow roll model predicts that this FNL is much smaller than order unity, and this is consistent, at least at the moment. But of course, this doesn't mean that the FNL of order 1 is excluded. Actually, maybe in the very near future, we may be able to actually detect this FNL of order 1. And as soon as you see this, as you observe this, then it means the standard single field slow roll inflation will be excluded. So assuming that such case might happen as well, and all these things sort of tells us, of course, maybe the single field slow roll inflation is okay in the end, but at the same time, maybe there are some elements of non-canonicality. So let's consider some inflation beyond standard model. So there are many proposals as long as one focuses on single field. At least there are several. One is to consider so-called non-canonical kinetic term, and which gives rise to some sound speed. Usually, in the canonical kinetic term, as you could see from this equation motion, the coefficient in front of omega square is 1, which means that they propagate at the speed of light. While if you change the kinetic term, then the coefficient can be smaller than 1. And that's the case of some non-canonical kinetic term models. We have some, and in this case, we know that this would induce some non-trivial non-Gaussianity of some particular form of non-Gaussianity. And because of this, we now have some constraints on CS. CS cannot be too small, but still, as you could see, the current data is not sort of so strongly constrained this model, and CS of say 0.1, which is very small in some sense, highly non-relativistic model, can still be allowed. You may have some non-minimal coupling to gravity. In this case, there are these issues of whether you should consider inflation in the original frame where you have this coupling, or you consider some conformal transformation and consider this in the Einstein frame. But in this single field slow roll inflation case, since phi square or phi moves very slowly, so actually it doesn't really matter which frame you consider. And anyway, the conclusion is that in this case, this tensor to scale ratio would be suppressed by 1/z for large z. This maybe this z phi square term, this looks exactly like the case of the Planck mass. Essentially, if instead of Planck mass square, you have the Planck mass square plus z phi square. So this actually means effective Planck mass becomes very large, and that gives this ratio to become smaller. Anyway, again, we cannot allow the small value of z, but as soon as z becomes very large, then everything is consistent. The only sort of unfortunate thing is that in this case, as you could see, the tensor to scale ratio becomes much smaller, and you lose I mean, you would not be able to see the this tensor perturbations. You may have some highly more non-trivial scale tensor theory. These days, people talk about so-called Horndeski model, where the only constraints on the theory is that the scalar field equations motion is second order. But in the variance in the Lagrangian level, you have higher derivative terms, and those higher derivative terms can make the tensor perturbation sound velocity to be less than 1 in this, let's say, in this original frame. And of course, at the linear perturbation level, you can always transform this theory into the sort of a quasi-Einstein frame, where the velocity of tensor field is 1. In any case, this is once you have this the fact that this sound velocity of the tensor mode or the space-time fluctuation can deviate from unity, then you have to really consider what the definition of inflation is. Another thing, of course, it's the most simplest sort of a extension of single field Slorol model is that you just consider multi-field models. And multi-field model may not be so uncommon. Let's say, as we know that in the early universe, especially in some string theory motivated or some other unified theory motivated models, there appears lots of scalar fields. So it is a quite conceivable that the multi-field plays quite important role during inflation. This can if the other, but if at each instant of time during inflation, if one field or one component of that multi-field plays important role, then the other components may be integrated out. This can give rise to some features in the potential. So this multi-field model may be in that sense, a origin or the some can give rise to some motivations for considering some potential with some features. There are some non-attractor inflation model and so on. Suppose I don't have time to touch today, but these are recent sort of topics which many people are interested in. Now, let's discuss some anomalies or some features which might sort of hint this non-canonicality. That in the first thing is on large scale anomaly. That if you look at the very large scale of CMB data, then the data point somewhat deviates from the predicted curve. And of course, on this very large scale, because of the large error bar, essentially due to the so-called cosmic variance, you cannot really make any definite statement. But still, this large-scale feature may be related to some non-canonicality of the inflation model. There are several other sort of features in the some slightly smaller scale, some oscillatory features, which might also mean something, some a contribution of some other fields. As I said, if once you integrate out some other fields, then those integrated out fields may give rise to some features in the potential, effective potential. And those effective potential might give rise to those oscillatory features. So in the end, maybe we may be able to see some trace of or the hints of this string landscape, so-called. But so far, we don't really know what to do at the moment. Now, going to a smaller scale, this is more interesting things we are discussing these days, is that maybe you may see something more interesting. And the point is that we have lots of constraints from so-called CMB scale or large scale structure scale, which is of order 1 gigaparsec, 10 to 28 centimeter scale. While if you go down to 1 parsec scale, which is about 10 to 18 centimeters, so the difference is 9 or 10 orders of magnitude difference. On those small scales, any initial fluctuations is essentially erased because of all these highly nonlinear fluctuations, the nonlinear physics after the universe became, let's say, matter dominated in these days. However, you may have some gravitational waves either coming from directly from during inflation, or maybe some may formed sometime after inflation. They may, because the gravitational waves do not interact with matter very weakly, they interact only weakly, they actually can come straight to our eyes today. Therefore, those small scale, since we now observe the gravitational wave by those LIGO variable interferometers and so on and so forth, we have a chance to see this. And one of them is this primordial black holes, and as we don't know anything about this, then we may assume that there is some, because of all this interaction with a field or multi-field sort of a phenomena, can cause some enhancement of the curvature perturbation on very small scale. And then these enhanced curvature perturbation, when they have actually represent the positive curvature, meaning that you have, this is the illustrative picture of, say, positive curvature, and the red line represent the horizon scale, Hubble horizon scale, and this is in comoving length picture. So comoving length is kept constant, and you have some fluctuations on scale much greater than the horizon scale. But during radiation dominance, let's say, the horizon scale increases and becomes the same as the same order as the scale of the fluctuation. At the time when the scale of fluctuation becomes equal to the Hubble horizon scale, if the amplitude of the curvature perturbation is order 1, this is the real curvature perturbation, the three-dimensional curvature is positive and order 1, then they can form a black hole. And this can be viewed as locally as a formation of a closed universe, because as we learn in the undergrad classes, then you have, say, three types of a topology of the universe. One is open or negative curvature. One is flat, it's Euclidean. One is closed. This is compact three-sphere. And a closed universe, once in radiation dominated closed universe, let's say, expands, but it reaches a maximum radius and eventually collapse. And a similar thing happens locally in this locally universe where the positive, there you have the positive curvature, and so positive curvature universe forms is collapsing, means that from outside, looking from outside, you are forming primordial black hole. And this tells you that the mass of black hole is the mass within that horizon at the time of horizon crossing, and which is given by about approximate by this formula. Essentially 1 parsec scale, a horizon scale, tells you gives rise to a solar mass primordial black hole. And if the scale is much smaller, the mass of black hole becomes much smaller. This is the observational constraints on the amount of primordial black hole. Interestingly, we have a very large sort of a regions of parameter space for small black hole, less than 10 to 12 solar mass down to 10 to 15 or 16 solar mass. You have essentially virtually no constraint, which means that our universe may be dominated by those black holes on the small mass. Maybe also they not totally dominated, but some fraction of a dark matter may be primary black holes on scale of 10 solar mass. And in this case, we expect that those LIGO, Virgo, and recently joined Kavli interferometers could the black holes found by those interferometers may be primordial, or part of that may be primordial. But anyway, this is the current status. And since I don't have much time, let's quickly go through its implications. So most important thing is that the gravitational wave appears. I mean, once you have these large curvature perturbations, then those large curvature perturbations do create gravitational waves as well. At the same time, they produce some primary black hole. The point is this: if you have some non-trivial curvature perturbations and some spectrum amplitude, and say a spectrum amplitude of 10 to minus 2, so it is much larger. By the way, the current large-scale CMB, the curvature perturbation amplitude is 10 to minus 9. So this would be 7 order magnitude enhancement. If you have such large enhanced curvature perturbation, then those curvature perturbation at second order, when they comes inside the horizon, start to oscillate and gives rise to secondary gravitational wave. And those secondary gravitational waves can, for example, be can be observed as a cosmic cosmic gravitational wave background. Now, at the same time, of course, when you have some fluctuations of the amplitude, whatever the fluctuations you have, there is always usually probability distribution have some tail. And if tail extend to, say, order 1 of fluctuation, then those order 1 fluctuation would form primary black holes. So this actually means that the mass of and the primary black hole mass, as I said, is determined by the scale of horizon at the time the scale cross the horizon. And also the frequency of gravitational wave produced will be also determined by the scale at the time of horizon crossing. Therefore, if you assume that there are some primary black holes in the current universe, whether it's a dark matter universe or some only a small fraction, there must be associated gravitational waves. And let's say if you primary black holes are called dark matter of the universe, then mass of black holes can be about 10 to 21 gram, and which correspond to frequency of 10 to minus 3 hertz. This is exactly the LISA band. If primary black hole, those black holes already discovered in LIGO Virgo interferometers, and then the mass would be about 10 solar mass. This would generate gravitational wave of 10 to minus 8 hertz. And this is almost so can be actually seen by this pulsar timing array observations. And the future prospect is that in the case of this dark matter model, then it independent of due to with some fairly simple but the analysis of including some non-Gaussianity, even if you have some non-Gaussianity in the initial fluctuations, then we find that the LISA sensitivity, the design sensitivity is sensitive enough to detect those background. And so the other way is that if we don't see such background as soon as LISA and Taiji and all these space interferometer project goes on, and they start to measure the gravitational wave from in the space, then we can actually exclude this model if we don't see any of those background fluctuations. there are some recent news from nanograph and so on, but I don't know how many time do I have. Maybe I have to finish now.
We have 5 minutes left.
Okay. So anyway, so now many people also know that these pulsar timing error people start to discuss. They say that they found some evidence of the background gravitational waves, but those background gravitational wave does not seem to fit well with the astrophysical origin. But if you assume it is a secondary gravitational wave produced by some enhanced curvature perturbation, then it seems to fit very well. The only issue is that in this case, the amplitude of the fluctuations seems to be quite large. Whether this can be allowed or this can really be the case is left for future study. So future issues, then, as I said in the beginning, first of all, we have to clarify what mean by inflation, how to get rid of this frame dependence. Of course, once we understand essentially the dynamics of inflation, of course, we are also interested in the initial condition before inflation, and that may be related to those string landscape things and so on and so forth. More physically, we still don't know how the universe was reheated, and if there's any way to observationally test this reheating, and that's another very important issue. I haven't had enough time to touch on this, but we may have some nonlinear or non-Gaussian effects during inflation, and that is considered to be very important these days. Related to this issue, that we have this or interesting sort of scenarios for primordial black hole formation and induced gravitational waves, and they may once we sort of start some evidence, we should be able to know how to discriminate different models or different scenarios. Maybe we be able to say some modifier. This is related to the initial definition of inflation, but effect of modified gravity and so on and so forth. But of course, I think in the end, all these, by studying all these things, we'd like to identify what caused inflation. Okay, thank you very much. Oh, sorry, this is the last slide. So this actually now that we are sort of entering the era where we are using inflation as a tool to explore physics for the early universe. So in that sense, it's we may actually consider the current or the future, the near future, as the era of the observational inflationary cosmology. Thank you very much.
Okay, thank you for the nice talk. Anybody in the audience, any questions? Please unmute yourself and ask. Okay, if not, I have a couple of small things to ask. So one of the things I was wondering about, so you mentioned that that when you take this R square term, what stops at R square, right? I mean, why don't I write out down something? So one of the reasons could be renormalizability, right? So we know that Einstein gravity is not renormalizable, but all the dimension 4 terms, let's say I write down R square, R mu square, and these kind of terms, I think in the past, people showed that these kind of theories are renormalizable in the sense that they don't have the pathological behavior of the Einstein gravity in UV, right? So probably renormalizability could be one criteria one can think about in the context of R square. I mean, stopping at.
I guess this is a case of pure gravity. Yes, as soon as you include the matter field, which is definitely the case because we have to have some standard model field anyway. I don't think it works.
But in the matter context also, we know that 't-Veltman condition gives us that dimension 4 terms are all removable, right?
I mean, you know, if you stop at R squared term, I mean, forget about maybe ghost problem and so on and so forth.
Yeah.
This is okay, but you cannot sort of, I mean, you cannot say it is a renormalizable in this. I don't know how to say it. Once you try to compute the corrections, quantum corrections, then you start to have some higher order terms anyway, right? I mean, you cannot really stop there. That's the whole point.
So
I mean, you may require it stops there. I don't know. I don't know about that. If that's the case, that's maybe a different story. But I myself don't know that. Yes, that's so maybe you're right, but I don't know.
Okay. And another question which I was curious about is that, so in all your presentation you have assumed Bunch-Davies vacuum, right? So could you tell us?
Yeah. I mean, no. By the way, so Bunch-Davies is not the correct word. Bunch-Davies is true only for some purely in a De Sitter space. I should call it adiabatic vacuum, and adiabatic vacuum is the most natural vacuum state. That's why I assumed it. But of course, yes, you may have some different. Maybe I should have included that possibility as well. That's true. Yes.
So what could be the main signatures in terms of what you present? For example, in your last slide, if I don't have adiabatic vacuum, what are the things one can look for?
Well, yeah, the simplest is that if you have some, let's say, go back to this kind of picture. If you have some kind of a transitional behavior, some non-trivial physics occurring sometime in the early stage of the inflation, I mean, from our point of view, then the vacuum state doesn't have to be the adiabatic vacuum. You may have some non-trivial vacuum. So that's one thing. Another thing is that the in this sort of a string landscape type thing, then you have a probability of having I don't have any picture, so it's this is, I mean, I'm not sure if it is. Let's say we are living some non-trivial vacuum, and in this case, this vacuum, of course, must be metastable, but still you can define what you call this Bunch-Davies vacuum. But at the same time, if the universe is purely De Sitter, then you have this one parameter family of vacuum states called alpha vacuum. You cannot sort of exclude such possibilities. If that's the case, and if that universe tunnels to some different universe, and the universe start to slowly, I mean, this inflaton start to roll down slowly, then for that universe, our universe, we will have a completely different initial condition. So that's something I'm interested in, although I haven't really done this computation yet. But that's another possibility, I think.
I see. Thank you. Any more question from the audience? Please unmute yourself and you can ask. Okay, if not, let's thank the speaker again. So thank you for the presentation.
Bye-bye.
And could you send us the slides for our seminar live?
Okay. All right. Yes.